Can you hear me?
Let me turn this on. Okay, wonderful. All right, yeah, thanks so much for putting on this workshop and asking me to be here. And my charge, as I understand it, is to get us all sort of on the same page so we can have a discussion in exactly 30 minutes from now about primordial non-Gaussianity. Okay, so let's really start back at the very beginning. So what we do in cosmology is we correlate stuff. We go out, we look at the night sky, we see a bunch of objects. These objects are not randomly distributed, but they have kind of interesting spatial correlations. And what we do as cosmologists is we trace these correlations through cosmic time. And by doing this, we learn about what is in the universe and how it evolved. And for the purposes of this discussion, the thing that we do that's interesting is we follow these correlations all the way back to sort of as far as we can look, which is the moment where the universe became thermalized, this so-called reheating surface. And what we imagine is that the fluctuations in matter that we see on this surface are one realization of sort of a draw of some underlying statistical probability distribution. And what we do by measuring correlations is we try to infer what that underlying probability distribution is at the reheating surface. Okay, so what do we actually know about this primordial density PDF? And we actually know quite a lot. What we know, if we decompose it into Fourier modes, is that the PDF is very close to being Gaussian, as described by this ratio of third to second moment. And what that also means is that the individual Fourier modes are very weakly correlated with each other. And we also know that as you change the Fourier mode, this PDF does not change very much. And oftentimes this is said that the power in density perturbations is very close to being scale invariant. So the width of this Gaussian does not change very much as you change the wave number. Okay. All right, so how do we interpret this? So famously, if we really take the structure of these correlations at face value, the fluctuations on the reheating surface look acausal in the sense that distances, points that have never been in causal contact are correlated with each other. And we take sort of the simplest possible interpretation of this surprising fact, which is that no one told us that this reheating surface was the beginning of time. And indeed, we think it's not. So we think the hot Big Bang where the universe reheated was not the beginning of time, and that there was some prior phase that explains the structure of the correlations that we measure on the reheating surface, okay? We give this prior epoch of the universe a name. We call it inflation. And what we imagine is that the universe was in a phase where it looked very close to being this exponentially expanding space called de Sitter space. And the reason we like this inflationary story is that it explains how the perturbations or the correlations that we see on the reheating surface could have arisen causally from local physics. And one point I want to make is that we don't actually directly see inflation. All we do is we infer the properties of this early universe phase through the structure of correlations we measure at the end of inflation. Okay, so this is going to be a talk about learning something about inflation by measuring primordial non-Gaussianity, so we should probably agree on a definition of inflation. So for me, what inflation is a theory of a really good clock coupled to gravity. Okay, what do I mean by that? What I mean is that there's something in the early universe that tells us what time it is. So there's some physics or some mechanism which is ticking along at some constant rate, where the rate here is specified by this scale I will call f pi for reasons that will become clear. And inflation is a really good clock in the sense that this thing keeps excellent time. It drifts by a few percent per Hubble time. So it really keeps fantastically good time. But what Heisenberg tells us is there's no such thing as a perfect clock. And so all clocks have to drift a little bit both in time and spatially. And the fluctuations in this clock can be thought of as a consequence of spontaneous symmetry breaking, or in very concrete terms, these fluctuations of the clock tell us that inflation ends at slightly different times in different areas of the universe and lead to the density fluctuations that we see at reheating. Okay, and so from my point of view, we should think of inflation as a process of spontaneous symmetry breaking. Okay. And the interesting thing about the fluctuations in this clock is that they get stretched by the inflationary dynamics. Okay, and the physics of inflation is quite interesting. the perturbations basically behave as though they are fluctuations of a harmonic oscillator with a time-dependent frequency, where the frequency is getting smaller in time. And so if you start with some fluctuation that gets stretched by the inflationary expansion, when it reaches a characteristic energy scale, which is the Hubble scale during inflation, it stops oscillating and freezes out. And what we measure are the fluctuations when they freeze out at the Hubble scale, which then propagate all the way to the end of inflation, where we measure them. And you can really view it as a harmonic oscillator whose frequency is slowly decreasing. So the state of the oscillator, some non-adiabatic event happens, and what we find is that the state of the oscillator is some very highly excited state when compared with the frequency at late times. And it's really these fluctuations that get frozen in that are telling us about the physics of inflation. And from this point of view, one of the really beautiful things about inflation is that modes all freeze when they reach a physical length scale, which is the Hubble scale, but fluctuations that start with different sizes require different amounts of stretching in order to hit the Hubble scale. And so what inflation does is it translates the physics of time into the physics of scale on the reheating surface. So fluctuations of different sizes require different amounts of inflation in order to freeze out. And so by looking at correlations on different length scales on this reheating surface, we're actually probing different moments during inflation. And so from this point of view, the near scale invariance that we measure of the 2-point function, say in the CMB, is telling us that whatever physics gave rise to inflation has to be very nearly time translation invariant. Okay, so we're really learning something about the time evolution of the physics that gave rise to fluctuations by measuring their spatial correlations. And for me, this is one of the most beautiful features of the physics of inflation. Okay. But one thing I want to emphasize is because this near scale invariance either implies or follows from the near time translation invariance of the dynamics, the information we currently have about inflation is really kinematics. It's telling us that whatever physics gave rise to the inflationary perturbations is very close to being time translation invariant, or said a different way, it tells us that the space-time that gave rise to these fluctuations are very close to being de Sitter space. And anytime you have this near time translation invariant physics or near de Sitter physics, you will get a nearly scale invariant 2-point function. And so we don't learn something about the microphysics driving inflation. Okay, so what we want to do is we want to probe the microphysics that actually generates the inflationary background rather than just studying how fluctuations evolve in this background. One way of thinking about it or conceptualizing it is what we're measuring are 2-point statistics. And it's like trying to figure out what the structure of the standard model is by only knowing what particles around and knowing what their propagators are. In order to figure out what the standard model, how it behaves, interacts, what you need to do is you need to collide particles with each other. Excuse me. Okay. And so what we want to do is we want to probe the interactions present during inflation. And what interactions do is they lead to higher point correlations. Okay. And the way that we measure or probe these higher point correlations or measure interactions is by measuring non-Gaussianities in the distribution of matter. Okay, so here, this is sort of the only very technical thing. I need to tell you how we summarize this information. And so the way that we capture the information about non-Gaussianities or higher point correlations is in the moments of this primordial probability distribution. So for concreteness, I'm only going to talk about the 3-point function. So here, the 3-point function in real space is just given by integrating over the probability distribution, as you would expect. And in cosmology, because everything is spatially translation invariant, it's very convenient to go to Fourier space. And so if we want to correlate density fluctuations at 3 points, it's convenient to do that by thinking about correlating 3 Fourier modes. Because of translation invariance, they have to form a triangle. And so we often parameterize the strength of correlations as a function of the shape of the triangle. Here's how we define it. And this 3-point correlation function as a function of 3 Fourier modes has both an overall amplitude, which we call FNL. So that's the parameter we want to measure. And then there's a shape dependence to this correlation as well. So the strength of correlations can change as you change the shape of this triangle. Okay. And the thing I really want to emphasize is that different types of inflationary physics give rise to shape functions or bispectra that peak in different kinematic configurations. So different physics will give rise to correlations that are strongest when the triangles take particular shapes. And that's why we give these FNL parameters different names. So for example, FNL equilateral corresponds to the amplitude of a shape which is largest when the three sides of the triangle are almost the same. Okay. And then we have other things like FNL local and FNL orthogonal, which we'll talk about. Okay, so the FNL equilateral is actually related to the sound speed of fluctuations of the inflaton in the simplest model. So it's actually a particularly interesting thing to measure. Okay, so given that we can probe the interactions of the inflaton, what are the things we actually want to learn? And to me, like the reason I'm a cosmologist is I want to understand the sort of the microphysics at highest energies. And so the sort of pressing question is, what is the underlying microphysics of inflation? That's the thing we want to understand. And what I'm telling you is the thing we kind of have access to are some low point moments of the probability distribution. So how should we even begin to organize our thinking about this question? How do we learn something qualitative about the microphysics of inflation? And like sort of good physicists, what we should do is we should focus on the energy scales present in the problem. So what are the energy scales present during inflation? So it has something to do with gravity. So M Planck has to appear, and very likely that's the highest scale in the problem. So we'll put it all the way at the top of the chart here. The other scales that have to be in the problem, there's this symmetry breaking scale, which is sort of the tick rate of this clock that is driving inflation. In this standard sort of conception of inflation as being driven by a field rolling at a potential, this tick rate is really just the speed that the field rolls. Okay, so that's some characteristic energy scale. And then the other important energy scale is basically the size of the universe, or the energy scale associated with the expansion of the background, which I told you is where fluctuations freeze out. And so that's really the scale at which we're probing the system. Okay. Okay. So the zeroth order thing you should ask is, have I even drawn these scales correctly, and where actually are they relative to M Planck? Or you could ask more directly, what is the energy scale of inflation? And I have to say, embarrassingly, I have no idea. The only thing I know is there's an upper bound on what the inflationary energy scale is, or the inflationary expansion rate has to be about less than 10 to the minus 6 times M Planck. And this is the reason why measuring tensor modes or B modes is particularly interesting, because it's a direct probe of the energy scale of inflation. One thing we do know from the measurement of the amplitude of temperature anisotropies in the CMB is the relative ratio between the Hubble scale and the symmetry breaking or clock tick rate scale. We know that this F pi is exactly 58 Hubble, okay, up to some small correction. And that's because the ratio of these scales is directly measured by the amplitude of scalar perturbations in the CMB. Okay, so we actually know that these two scales are in this order, and by how much. But because we don't know the overall scale, you could imagine sliding this up and down on this plot. Okay. Okay, good. So now we have to understand how to parameterize the microphysics of inflation. So we don't fundamentally know what the underlying physics driving inflation is. It could be just a field rolling in a potential, like in many models. It could be something involving string theory. It could be some very strongly coupled physics. We don't really know. And I think given sort of our lack of knowledge, what we should do is to try to make qualitative inferences about the underlying physics. And an interesting qualitative distinction is whether the physics driving inflation is strongly or weakly coupled, or becomes strongly or weakly coupled before it gets UV completed. Okay. And so in order to parameterize this, there's actually another scale that we can put on this plot, which is the strength of interactions of the inflaton with itself, this so-called strong coupling scale. So this is the energy scale at which the physics of the inflaton becomes non-perturbative. And here, because of the non-detections of non-Gaussianity, we actually have a lower bound on what this scale is. So as this scale gets higher, inflation gets more and more weakly coupled. And so what we know is that this scale has to be higher than about 10 Hubble at present. Okay, and here's the conversion between FNL equilateral and this scale, if you like. So now there's a qualitatively interesting threshold, which is we learned something qualitatively new if we can push this threshold above F pi. Okay, so now there are sort of two possibilities. Either this lambda scale sits below F pi, or it sits above F pi. And if this scale is below F pi, so that tells us that inflation becomes strongly coupled before new physics enters. in that sense, it's somewhat like sort of the technicolor completion of the physics of the standard model, or from a more condensed matter point of view, it's kind of like a type 2 superconductor. Or it could be that inflation is weakly coupled all the way to where new physics enters. And in that case, it's kind of like the Higgs UV completion of the standard model, or like a type 1 superconductor. And so we learned something qualitatively new when we pass this threshold, okay? And if we want to translate that into an FNL parameter, this crossover between strong and weak coupling happens when FNL equilateral is about 1. Okay, so there's some sharp theoretical threshold, but it's roughly around 1. And so if you can push FNL equilateral below 1, you learn something qualitatively new. Of course, that is a challenge, but I think we could view it as an opportunity for theory. Okay, so this is why measuring FNL equilateral is interesting. It tells you about the underlying nature of inflation. Okay, so if you slept until now, here's the one slide takeaway. Equilateral non-Gaussianity, interesting, probes self-coupling of the inflaton, threshold FNL equilateral 1. Okay, what's another qualitative question we could ask? Is the inflaton the only degree of freedom that's important during inflation? Like, is it alone? So if you think inflation is something stringy, or maybe it has something to do with extra dimensions, there could be new states around whose masses are of order the Hubble scale. Okay, and that could be some new scale in the problem. And you could imagine trying to probe these states whose masses are somewhere in the range of Hubble. Okay, so this is kind of a totally plausible thing given what we know about UV physics. But now you can ask, how would we go about looking for it? So there's this interesting fact that in single field inflation, non-Gaussianity and this so-called squeeze limit, where you correlate two very long wavelength modes with two very short wavelength modes with a long wavelength mode, vanishes exactly. Okay, there's some fine print, you can ask me about it afterwards. But roughly speaking, for this argument, FNL local in single field inflation, you can think of it as being 0. And so if you're able to detect FNL local, this is highly suggestive that there are additional particles around that contribute to the density perturbations in matter in the early universe. Okay, so this is one way to imagine probing the existence of additional states beyond the inflaton. And if you are so lucky as to measure FNL local and start to infer that there should be additional states, you can imagine trying to do more refined things, like figure out what their mass is or what their spin is. Okay, so there's this interesting fact that inflation is kind of like a thermal bath. And so it generates particles that have masses of order Hubble or less. Okay, and the production of these particles, they can then decay into the things that we see, and they can leave subtle imprints in the things that we actually measure in the late universe. And these correlations, or these imprints in the correlations, allow us to extract information about these underlying particles. And one way of saying it is that just measuring FNL local itself is sort of a coarse measurement of the imprint of additional particles present during inflation. But if you're able to measure the entire shape, so the entire way that correlations change as you change the shape of this triangle, there are more detailed signatures in these correlation shapes. And so one example is the following. So imagine that you produce a massive particle during inflation, which then decays. And it can leave a signature in the 3-point function of matter fluctuations at late times. And if the particle is sufficiently massive, what you will find is that as you approach this very squeezed limit from the equilateral configuration, there's a characteristic oscillatory feature, which I've plotted here on the right. So as you think of this as a function of the squeezing of the triangle, this characteristic ringing appears. And the interesting thing is that this characteristic ringing is literally the oscillatory behavior of a propagating massive particle. And so if you can measure this oscillatory phase, you can actually do some kind of spectroscopy and extract the mass of the particle. Okay, so this all sounds very futuristic, but people are actually really starting to try to do this, like including people in the room, both in large-scale structure data and in the CMB. So I think it's a very intriguing thing. It really is the promise of using inflation as an extremely high-energy particle collider with reach far beyond what you could imagine doing here on Earth. But I think really doing this correctly and carefully requires new calculations on the theory front. It requires development in large-scale structure theory. It requires developments in data analysis. So I think it's a good opportunity for us to all work together. And I think this is so important that this is really what I spend most of my time doing. So this is really kind of my day job, is understanding how to calculate these signatures. So I'm happy to talk more about it. Okay, so two more things I just want to mention just to say. Okay, so here again, if you kind of like zoned out for a minute. So local non-Gaussianity probes additional states beyond the inflaton. Here, there's not a sharp threshold, unfortunately, but there's a qualitative benchmark, again, around FNL local around 1. You'll find in practice, it's like rather difficult to model build FNL local smaller than 1 in practical examples. And so again, if you can push this below 1, you kind of learn something qualitatively new. But I want to emphasize for FNL equilateral, there's a like sharp theoretical threshold. Here it's a little bit fuzzier. Okay. Okay, so two other things I want to say. We also can coarsely probe the initial conditions at the beginning of inflation. So what we believe is that the fluctuations that are generated, or the correlations that are generated by inflation, are quantum mechanical fluctuations. And the sort of minimal assumption you can make is that these things started in their ground state at the beginning of inflation. So that's like a totally reasonable, this is as a practical matter what almost everyone does when they calculate these things. And the nice thing about things starting in their quantum mechanical ground state is that the correlations are totally regular in this kind of peculiar folded limit, where you take the limit where you squash one of the sides of the triangle. But if you start the fluctuations in some excited initial state, or you have a bunch of actual classical particles in the initial state, what you will find is that this folded configuration of non-Gaussianity has a very large signal. And so measuring this folded type non-Gaussianity is, in a sense, a probe of the initial conditions of inflation. Again, unfortunately, here I don't have a sharp threshold for you, but this is sort of why it's interesting. And then one other thing I should say is people tell me that apparently there's more to life than correlation functions and moments of a distribution. I'm not sure I believe them yet, but what we know is that correlation functions or moments really capture the properties of a probability distribution near the peak of the distribution. But it's possible that there are observables that are actually quite sensitive to the tails of the distribution. And the moment expansion really is quite bad at capturing this information. And so I think this is a challenge both for theory and data analysis. One, from the theory side, to understand how to summarize the information very far out on the distribution in an efficient way and calculate it. And then on the data side, to figure out what the right probes of this part of the distribution are. Okay, so that's roughly everything I wanted to say. Let me just sort of summarize what, to my mind, are the sort of 0th order targets or interesting things to measure. So two things that I really did not emphasize but are important. So at a 0th order, it's important to know what the energy scale of inflation is. That's why measuring B modes is interesting. There's a very interesting question, which is, I drew a bunch of energy scales on a plot. Are those all the energy scales around? And measuring primordial features is a probe of whether there are other interesting and important energy scales or thresholds. So to me, that's why that's an interesting thing to do, and I think we'll talk more about it. From the perspective of 3-point non-Gaussianity, I think the two questions that, sort of conceptual questions that it addresses are, one, what is the strong coupling scale of inflation? And measuring equilateral non-Gaussianity is a probe of the strong coupling scale of inflation. And there's this interesting threshold at FNL equilateral of order 1, which you can conceptually think of as the crossover between slow roll-like inflation and non-slow roll-like inflation. And then the other sort of conceptual question is, are there other degrees of freedom besides the inflaton that are important during inflation? And this is probed by local FNL. And there's sort of a benchmark FNL local of order 1, where you can imagine learning something qualitatively new by pushing below this threshold. And if we are so lucky as to infer the presence of new particles, then the types of things we'll want to know are, what are the mass and spin of these new particles? And that requires these sort of cosmological collider or particle non-Gaussianity kind of templates. Okay, so that's all I wanted to say. I'm happy to take any questions.
Houston, very
Hey.
nice talk. If we do detect FNL equilateral, let's say 50, can we say something about the number of fields?
If you measure FNL equilateral at 50?
Yeah.
I think it's model dependent. Do you have something particular in mind?
Well, you see, there is this nice statement that we can make about FNL local, right? If we detect
Yes.
it should be multi-field.
Sure.
You know, FNL equilateral typically appears in single field models.
Yes,
right?
yes.
But probably there are multi-field models that also produce FNL equilateral, right?
Sure, yes.
So we cannot make any.
I don't think there's a sharp statement to be made, no.
Thank you, Austin. That was really nice and has clarified a lot of things I was puzzled about by inflation for a long time. So coming to what you said about the scale invariant nature of the 2-point function telling you about time translation invariance, we know that to have baryogenesis, you have to have CP violation. CP violation implies T violation because CPT. So is the slight deviation from scale invariance of the power spectrum, you know, the NS minus 1, is that actually, should we be thinking of that as telling us something about the level of T violation and therefore telling us something about the CP violation?
Not in a sharp way that I'm aware of. So I want to distinguish two things. So here, the scale invariance is related to sort of a continuous symmetry, which is time translation invariance. The CPT in the CPT theorem is time reversal, which is a discrete symmetry. And these two things don't necessarily have to have anything to do with each other.
So I think you had like a target for the curvaton. Is that like a sharp target or?
Yeah, so this is sort of like in okay, let's say the simplest curvaton models. This is sort of a lower bound to how much non-Gaussianity you can get from the curvaton. Yeah, I mean, there's no totally sharp thing, but if you wanted kind of a maybe something to shoot for, this is something of order 1 that's totally concrete, but it's in small print because I'm not super strongly, but it's like I was charged with finding some targets, so I wanted to suggest some targets.
I was just wondering if you could say some of the examples. I think it was the heavy tails and other things. You said where FNL local, or sorry, reaching the threshold FNL equilateral order 1 opportunity for theory. Can you say more what you have and what you mean by that?
Yeah, so I think I mean basically what Misha was talking about this morning. So I think in order to measure FNL equilateral, it's going to require a lot of theoretical modeling of large scale structure. I guess it's an opportunity for you as well. And I think it's I think it's the type of thing that probably people like me should also be interested in. It's an interesting theoretical challenge, and it's an important one, I think.
Thanks.
One more. Let's thank Austin again.
Thanks.
Ben, can you hear us? Ben one's out.
Yes, I can hear you.
Great, thank you.
Hi, everyone.
Where does this,
This thing. So you
So I
put
just
that
hold
around
it.
your ear? Do you want to?
okay, okay, can I?
Just pass it around.
Okay, sounds good. We
Okay, so we're gonna get started with the panel. I'm just gonna lay out the ground rules, and then we can go from there. So I have told these panelists that they have 5 minutes to present what they're either most excited about and or most worried about with the measurement of non-Gaussianity and large-scale structure. So they're each gonna present their point of view on that question. Then we're gonna have 30 minutes of moderated discussion. So I will ask the questions, but the audience, if you have follow-up to those topics, so if someone says something provocative and you want more information, please throw up your hand and we can have follow-up. But off-topic questions, we're going to save to the last 10 minutes. The last 10 minutes is then open to audience questions. So save your, I really want to know this, but no one's talking about a question for the last 10 minutes. Okay, so I think we're ready to go. So we're going to start with Olivier Doré, who's going to tell us his most excited, worried question.
Okay. All right. Thanks, Don. Hi, everyone. So, all right. So I'll give you a quick update. I've been asked this question many times already today. So I'll give you a quick status about SphereX. Shen tomorrow will speak tomorrow. We'll give you a little more details. So I guess the status is summarized by these two pictures that you see here on the left. On the left is a telescope, what we call the payload telescope instrument, the thermal cooling system out of February 2024. So a couple of months ago, in the Caltech basement. And right after this picture, it was shipped to the Ball Aerospace facility, BAE, no, whatever, and assembled with the rest of the spacecraft. And this picture was taken last week. And this was the first assembly of the full spacecraft. So now it's fully assembled and it's gonna be tested for the coming months. And so it's happening, it's real. You can touch it, well, not really, but almost. And the key thing you should remember also is the launch is scheduled for February 27th, 2025. So less than about 10 months from now, and it's on schedule. It has been this date for several years now, so we are on schedule. And if you want to see it, you can go see it. It's going to be from Vandenberg Space Force Base, which is about 1 hour north of Santa Barbara in California. So it's driving distance from here. And you can see it from pretty much anywhere there. So you should plan on that. Okay. And another fact about this instrument, about SphereX, is so far in the lab, all the instrument performances are in agreement and match actually our most optimistic forecast as compared to, when we compare to what was in proposal, the CBE values, if you speak this language. But anyway, so instrument development is on schedule and performances are met. Okay, you can check out our website. You find many more information, cool picture, regular updates. To set up this discussion, our target for FNL is still sigma, is FNL at lower than 1 at 2 sigma, right? FNL lower, well, I guess I didn't write it correctly, but our errors of FNL would be of order 1 at 2 sigma. That's still our target for FNL. Local, yes. Using power spectrum and bispectrum. Good, important point, not orthogonal. All right, list of most exciting aspects on the most worrisome aspect. So the most exciting aspect, as Austin said very clearly, I think for me, measuring PNG is one of the very few observables, really new observables we have about inflation. So we can measure it. So we have to push as hard as we can. And the other main observable being R. As we just heard, it said different things. So we really have to push as hard as we can on FNL. And exciting aspect, of course, that we are about to enter a new regime observationally with SphereX and then DAISY and then or DAISY and then SphereX and then Mega Mapper. So that's a lot of progress. We will see a lot of progress in the coming years. Most worrisome aspects, of course, are first, for me, can we handle systematics on large scales? All the measurements so far are systematic, largely systematic dominated on large scales. Can we do better? And some you can control by instrument design, but a lot of the systematics are also intrinsic to this measurement. I have to do with the sky, for example, dust extinction, stellar contamination. All this will be present in all data sets, no matter what you do, no matter how good your design is, no matter how performant your design is. Others you can correlate better, calibration, you can, control better like calibration effects, but nonetheless, systematic will be hard to handle, and it's true for spherex also, of course. It's important also to notice that many of these systematics will be correlated from survey to survey. So we often hear about cross-correlation would solve everything. That's not true. So cross-correlation across survey, journal analysis across survey won't necessarily be a panacea because systematics will be correlated by nature, some of them. Another aspect which is worrisome, and we actively, Chen will tell you more about it, and others are working on it too here, is modeling on large scale is actually not really mature. Like there are a lot of details which have not been put together and that are really subtle. GR correction, wide-angle effects. I think we are working hard on that. I think we have it now under control with the past spectra, but it really has not been done for the bispectra, and it is necessary. So I think, and we need more. We need several papers, several studies. We need to cross-check results. So I think it's a call for help. I think that's a real challenge. And as we heard this morning from Oliver, these effects are not small, right? They are order FNL of 1, right? This GR term will contribute a signal which looks like FNL, a signal which is 1 over k² of amplitude 1. So in any case, we should measure something, and then we'll have to subtract this template and then go for the primordial template. But so we have to be very careful, and there are papers which are in disagreement. Some of them are wrong. So it's not mature at all. It's not it's not like a CMB. So we have to be very careful. And big important question, of course, is can we measure FNL at all, right? We heard this morning the signal we measure is proportional to B phi. What we really measure is B phi FNL. The relation between B1 and B phi is more complicated. It was really emphasized recently in literature that the relation between B1 and B phi is really not linear. There are other, let's say, second order effects that complicate this relation. Can we break this degeneracy between B phi and FNL? And it's something we really want to do. There have been several studies in literature showing that if you can really break this degeneracy, you can actually gain a lot because you can leverage this B phi dimension to do multi-tracer analysis, and that's really powerful. You can get extra factor few in sensitivity, but you really have to do that in a not do that theoretically, but do that in practical sense, finding a proxy for B phi using your data. And so that's something which has to be demonstrated and has not been proposed even. So that's very important. And an important fact is that we need to address all these questions in the coming years. There is no data are coming. Data will be spherex. This data will reach this point in 2 or 3 years from now. So we really need quantitative and thorough answers to all these questions. And that's my worries. Thank you.
Thanks. Next up, Marlena Laverde.
So let me start by saying that I think a lot of the stuff that Austin addressed, many of the things that I find very exciting about this, all of these different non-Gaussianities, different features, local, equilateral, beyond, and I share many of Olivier's concerns as well. But I just wanted to address something related, which is that this one of the main signatures that we look for in galaxy surveys to constrain non-Gaussianity, and the reason that we will have stronger constraints, we believe, from FNL local is because of this nice discovery by Neil and Olivier and Dragan and others that primordial non-Gaussianity can imprint this correlation between local observables, here represented by that little tiny box, which is an N-body simulation movie from Andrei Kravtsov, making those small scale observables correlate with the large scale gravitational potential. And so we don't think that that's something that can be generated in any way other than through initial conditions once, at late times. And then the nice thing about this is that we don't actually need particularly good models of our observables. We just need to know that they are modulated by a large scale potential. But this thinking has led us quite far to think of this as a very exciting probe that we can use to robustly identify signatures of something inflationary. But there are other lines. One can generalize this lines of thinking to look for other sources of new physics that might imprint something on scales that are large compared to the nonlinear scale or the typical distance that particles can travel, like cold dark matter particles travel. And so examples of that are if I have some dynamical dark energy with a clustering scale, which is Hubble or slightly smaller than Hubble if it has a sound speed, or neutrinos that we know exist, or some large component of radiation. All of these imprint new scales in a problem that are large compared to the nonlinear scale. And this general type of thinking that if there's a separation of scales between these two things, that we can imprint correlations and observables that have an imprint of this new physics at large scales. So I think I am excited about thinking about this type of observables beyond non-Gaussianity to test other things about new physics. For instance, isocurvature or other stuff that has some clustering on large scales. And I think that this framing is a nice way to think about observables. It also offers it's an opportunity to detect these things, but it also could confuse us only once we start approaching these thresholds of FNL of order 1, then one can have other imprints that of known physics. So here's some examples of neutrinos or fluctuations in the ionizing radiation, which can propagate over Hubble scale distances and cause some modulation of galaxies on Hubble scale distances. So these are also scenarios that, I think once we get to these next, I am also concerned that of the many things, the B5 modeling, the observational systematics on the sky, and also astrophysical modeling, that once we approach FNL of order 1, there are things that we have to worry about that we haven't. And my PhD student, Charuhas Shivashwarkar, will give a short talk on some of these things tomorrow. Ben, or is Ben next?
Yep, Ben's next. Hi, everyone.
Ben, do you need me to adjust your slides? I mean, can you screen share, or do you want me to push go on the slides?
I assume that you'd be showing, or that they'd be shown somehow because you invited me to upload them on that.
Okay, just tell me when to go to the next slide.
All right, great. Okay, so next slide. Thank you. All right, so what am I excited about? I mean, it goes without saying that I'm excited about the potential of non-Gaussianity studies with large-scale structure, and specifically spectroscopic surveys. The 3D mapping that they will give just opens up new opportunities for non-Gaussianity studies that are complementary to the CMB. So we're looking at these higher order statistics and various summaries to find out what we can learn. One thing that I find surprising about all this, and which we're trying to remedy, is that nobody knows how much information 1 gigaparsec cube of universe actually contains about primordial non-Gaussianity. Now, this may be surprising because we hear all these forecasts. These forecasts are typically about individual summary statistics. So, we just heard Olivier's forecast for CRX. That's for a particular summary. We've tried in using simulations, we've tried to answer this question, which is I think it's a theoretical question, really. What is the information content of 1 gigaparsec cube of universe? Starting with the dark matter, which is not directly accessible to observation, of course, but then going to halos and then sort of working our way through to galaxies, mock galaxies, and like properly simulated surveys. We're not there yet, but so we're making some progress with going through power spectrum, bispectrum, marked versions of those, the halo mass function, which is also not directly observable. Then there are other statistics that others have tried, like KNNs, wavelets, and I've put down a bunch of archive numbers at the bottom if you're interested in looking at any of those. And all those papers try to answer the question, how much information is in these statistics? We try to push even further. I think ultimately we'd like to know how much information is there, period, not just in one particular summary. If we had infinite computing time and infinitely accurate models and large amounts of training data for neural networks and so forth, we could ultimately probably get that information down to some smoothing scale and ask how much information does 1 gigaparsec of dark matter or of galaxies, etc., actually contain. But currently, we're actually not ready yet for that. And that's partially because just a brute force, kind of straightforward application of neural networks to this problem doesn't work yet. And the reason is, I think currently that we just don't have enough training data for the moment to do this kind of in a brute force way. We're trying to think of other ways to do this. If you go to the next slide. So you may know something about me, which is that I'm interested in applications of AI or machine learning to cosmological and fundamental physics questions. And so I thought this would be fun to highlight that in this context, actually, there's one thing we learned from AI. It's not often foregrounded in papers, but I know that sometimes we actually discover something using these techniques and then later validate them with more classical approaches. So this is, for this paper, actually, we all agreed that we wanted to put this into the abstract and say that this is something we noticed just by training a graph neural network to extract information about this, in this case, local FNL from simulated data. We found that that did a lot better than looking at two-point correlation functions. And we realized that this had something to do with the fact that it had access to the halo masses involved in the data that it was analyzing. And then we tried to just look at that with more classical statistics. If you go to the next slide, please. So this is a comparison with so this is the object of study here was this B-phi degeneracy that Olivier also mentioned. And it turned out that we seemed to be able to get some information about FNL if we knew the halo masses, and then we're giving those to the neural network. So looking at the halo mass function, we found similar, a similar breaking of the degeneracy. So halo mass combinations of the halo mass function and second and third order statistics give us break that is, and depending on how much information you give it, what the smaller scale is that you push to in these simulations, you break this more and more strongly. At a level that is not too dissimilar, sort of order 1 from the case where you just assume B-phi to be externally fixed by theory, for example. If you go to the next slide. So in a follow-up study by Fondi et al., a PhD student in Licha Verde's group at Barcelona, it seemed that this generalized from studying halos, which is obviously idealized, to galaxies, as long as we had information about the galaxies that we could use to guess something about the host halo formation redshift. And so here's just one result from the study showing that compared to an ideal situation in these orange error forecasts, we get with statistical or systematic errors based on the quality of the model of the formation redshift based on the available photometry, we could get some, but we could still break this degeneracy and get some constraints on FNL that are only mildly worse than what you would get in an ideal case. So yeah, those are the slides that I prepared. So I'm excited about these new techniques for getting at cosmological information based on simulations, but there are of course many challenges, and I think at the moment we're not quite ready for prime time in terms of actually applying this to real data, but we're working our way towards that because, at least in principle, these techniques can capture nonlinear evolution and complex biasing models that would be very difficult to do in an analytical or semi-analytical way. So there are, but there are also interesting hybrid approaches that we're exploring between combining perturbation theory and machine learning. And then another challenge will be to scale this to the data set sizes, that we will get with Spherex, DESI, already, Euclid, etc. So yeah, let me end on that.
I'm the lazy one that doesn't have slides. but I'm also the one that's going last, and so I don't want to be too repetitive. So the question was, what I find exciting, or what I find nerve-wracking, maybe it would be the word, about primordial non-Gaussianity. So obviously the window into the early universe, and we just heard a beautiful summary of all of the physics that is encoded in the 3-point function, not just the local type, but the equilateral, and especially the orthogonal. So I think that's just fantastic. It's the one fossil we know we have from, the beginning of the Big Bang. We hope we will get the gravitational waves, but we may or may not get them. We have this fossil, we can study it, encodes all of this information that we heard about. So I think it cannot be more exciting. So in addition to that, the effect is really small, right? FNL equilateral of order 1, which is kind of, I think, extremely good target, that corresponds to something like a part in 1,000 of the tree-level bispectrum of produced by just the gravitational evolution. So the effect is really small. And so that's really great. It will require a very ambitious survey, as we've heard this morning, huge volume, controls of systematics, all kind of things. So obviously, we will learn a lot about the early universe and about astrophysics if we manage to get such a survey. So that's also very exciting. It's also extremely ambitious theoretically, I think. It requires, just to make an order of magnitude improvement about from what we know from the CMB, it requires this sub-percent precision of things to theoretically to have. That's very challenging for perturbative methods. It's very challenging for simulations, for machine learning. It's very challenging for everybody. So I think that the fact that this is very ambitious, I think it's opens a very exciting opportunity. For all of us that are more interested in theoretical things, the fact that a lot of the information we are after is close to the nonlinear regime, or is affected by galaxy formation. So it opens up questions: how can we do this in a way that is robust, or that we can believe in it if we get a detection? I mean, we all suffer from bicep syndrome, maybe. So I think. So there's also plenty of opportunities to calculate new things, higher loops, other statistics, machine learning. So for theorists, I think this is, it opens up a lot of opportunities, and we will need to understand galaxy formation very, very well in order to pull this off. So I think that those are all, I think, very exciting things. So what is challenging, I think, is pretty much the same list. You can spin it, in one way or another. You can say we have access to this early universe. It's great. I'm so excited about it. But of course, the physics of the early universe is super speculative. So there is no real target that anybody, I mean, there is a theoretical target of the FNL equilateral, but there's not a target that there will be a signal. It's a target that we might learn something. But if we spend 20 years and we we didn't see anything, and that means that the energy scale is great, but, it's less interesting than if we see something. And there's, I think, no guarantee that we will see something, just as there is no guarantee that we will see tensor mode. So you can spin, I think, all of these things however way you want. Similarly, all of these things about the need for theoretical control, you can spin it around and say, as you make these calculations more and more precise, you have more and more of these nuisance parameters. They eat up most of the statistical information in your survey. It's just to measure B gamma 3. Who cares about B gamma 3? So you can spin things in both ways. You can be bad, or you can say, okay, we will learn about galaxy formation. We will learn about any, astrophysics that it's involved. So, I've been involved mainly in the perturbation theory, EFT side of things. There are many questions there related, for example, on this large number of nuisance parameters. Are they real? Is this a fake? If we had a better model, could we get away with not having so much freedom? I tend to think no, but I would love to be proven wrong. But so you can say definitely, as the signals that we are going after are smaller and smaller, the place where these signals are going to be comparable to the theoretical errors is going to move to even larger and larger scales. So the idea of doing things perturbatively becomes better and better. That would be one way of saying things. On the other hand, the information about these bias parameters in galaxy formation is coming from smaller and smaller scales. And how much do we believe these biasing prescriptions, or are they both at the same time flexible enough, but are they too flexible? How do we test this? If we test this with simulations, simulations are not real simulations. They are like informed, models with a lot of freedom, subgrid physics freedom that we don't really control. So there's a lot of interesting questions there. I think it's clearly a very ambitious project from an observational and theoretical point of view. I think it's great. It will depend on the young and ambitious people in the room to push this forward and calculate all of these things and show that it can be done. And I think it's the ambitious project that can really, make the young people excited and join the field and move forward. So I think that is another thing that that makes me, very, very happy about this kind of project. So I'll stop there.
Can people hear me? Okay. I have prepared some questions. I have told the panelists, Ben, this is the first you're going to hear about it, that they are allowed to decline to answer, but I will point fingers if no one wants to answer. Everyone can answer if the question is interesting, so we'll see how it goes. So my first, in line with Matthias's built-in pessimism or bicep life experience, I wanted to ask the panelists what it would take for them to believe a detection. So let's imagine any scenario you like, where in several years we have something called a detection of non-Gaussianity, pick your flavor, and what would make you believe that result was true? Or what work could we do that would make you believe that result was true? Do we have who's got the microphone? In large scale structure or in cross correlation, if that's the angle you want to take.
All right, okay. Yeah, fair enough. Well, I think it's just, the way science should be. It's going to be, I think, my personal attitude would be like you need several teams with the same data set. You need the data to be public. Several teams analyzing the data in a transparent way, all codes public, and then ultimately after that, several probes. Hopefully, it can be 7 cross correlations. For example, you can imagine a bispectrum galaxy, bispectrum of galaxy clustering. We see something, then of course, it has to be consistent with power spectrum, but then you would look for the KSZ cross correlation, which would be very powerful. And then it would maybe after that another data set. I think we need several groups, several data sets, several probes. I think that's a must. And if we don't have that, it's going to be hard to have. I think it's going to be a difficult measurement no matter what. And if we don't have that, it's going to be hard to have a really trustworthy results. I mean, yeah.
So we're trying to build one giant project, which will be called SpecS5. So does that mean we need 2 giant projects? Like if that's the goal, or does that limit what kind of non-Gaussianity you believe?
Well, I mean, if it's the same, imagine if this depends on how it compares with, for example, SpherX and others. If it's the same sensitivity as SpherX, you need 1, it will be 2. Then that's you're good. I think you don't need an extra one, but it depends on how they complement one another. But I think, yeah, if you imagine you have this and you have the SO/S4 cross correlation with the KSZ signal, that becomes really, then it really reduces substantially the systematic freedom. And if everything is consistent, then it's become solid. That's my hope. Yeah.
Marlena, did you?
I think I agree, and I think I agree with everything Olivier said. It makes me think of one, concern, which could be that that we just have, in order to have something that everybody believes, we have to have these really flexible models, and then we don't see a signal, that we can't, that we don't develop good enough models to actually ever convince ourselves of FNL of order 1. That would be one concern I would have added to my slides. But I think the multiple analyses, and particular multiple probes, like splits of the data, splits of the galaxy population, it seems challenging, but I would think that would be needed.
Yeah, I think I'm a bit optimistic in the following sense. If we just take the bicep example, obviously this would be a tremendously interesting, claim, and everybody will jump to try to do it. And reanalyze, as long as the data is public, and even if the data was not public, like in the case of bicep, it was still. So I think we're pretty good at finding the mistakes of each other, because especially in this high stakes kind of game. So I'm pretty sure that if there is a mistake, it will be found, or if there are reasons to be doubtful about it, or what is the leading reason why I shouldn't believe it. And then we can make some progress once this has been identified, if it's not that a mistake has been found, but like some reason to be skeptical has been found. So in that sense, I'm optimistic, but I think it takes several iterations.
Ben, did you have comments?
Yeah, I mean, I agree with everything that's been said before, but maybe I'll add one thing, which is that sometimes in the past, just requiring at least 3 sigma for a result has saved us from making exaggerated claims, or like coming to conclusions. Let's put it this way, and so we're always going to be interested in the data at the bleeding edge, squeezing it for everything we can get out of it. But just having a high significance result, in addition to all of the checks, because that's the only thing that then allows you to split your data in multiple ways and look at it and still have enough significance and enough information to actually test whether the result is robust. So in that sense, so my advice for your survey is make it big. Make sure that there is, you're covering a huge amount of volume with as high resolution as you can, so that at least in theory you're ready for a high significance result. Of course, the problem is we don't know what the signal is, so that's the downside. But if we were going to make a claim, for example, of detecting FNL of 1, I think the error bar should be much less than 1 in order to really be able to make that claim. The statistical error bar, and then the systematic error bar can be studied if you have such a small statistical error bar.
Okay, thanks. Okay, I'm going to move on to the next question. Okay, so there's been a varying attitude in the literature towards the value of going to higher redshift. So specifically, we heard about the goal for Spec S5 was the number of linear modes, but the definition of linear modes as you go to high redshift depends on assumptions about particularly biasing and things, how nonlinear your objects or your targets are. So I wanted to ask if there were, what was your attitude towards the value, particularly about avoiding nonlinearity at high redshift? Is it all redshifts are the same? Is high redshift where we need to go? I'm guessing everyone's going to be somewhere in the middle, but does anyone want to stake a position?
Okay. I agree that the assumption of how bias evolves means that the high redshift tracers are going to be more biased, and we have to worry more, or we have to, not necessarily more, but we don't, if you have stable clustering, then you don't actually gain in some sense there. We do get more volume. I don't have a sharp answer to this question. I think it's interesting. I can't imagine that we shouldn't try at high redshift.
Yeah, I guess the The issue is, for example, the F-sky versus redshift, right? Like F-sky, you don't go to deeper redshift. It's the same level of nonlinearity, but you increase the number of modes. So if you're just maxing out modes and you do this counting, it affects what you think is the right survey strategy. So it sounds like everyone agrees that because of biasing being equally large under most of assumptions, that there's no particular advantage, at least in terms of modeling a high redshift. Is that the consensus?
I mean, it maybe connects to what I was saying before. If the survey really has a huge amount of sensitivity, you could aim at just finding the fainter, the smaller objects, even at the higher redshift. So those are going to be, they're not going to be the most biased objects. If you can see things at a high redshift because they're the brightest things around, then they're probably also the most biased. But the idea would be to go and see faint things at high redshifts.
Independently of I think the answer might be in the detail of the forecast and the detail of the EFT parameters you margin over, etc. So maybe you have to run a number, but there is value also in probing a different redshift range, independent volume, and you can. If you see something at low redshift, you also have to see, if it's primordial, you have to see it at high redshift, and that's super valuable. You don't want necessarily to repeat exactly the same. It might be smarter to just probe an independent volume instead of repeating the low redshift, which has been covered already. So there is great value in that also, independently of the detail of the nonlinear scale assumptions. I think can be ignored. Yeah.
Okay, I'll go to my next question, which you can keep the mic because it's for Olivier specifically. So you showed the forecasts were for power spectrum plus bispectrum for FNL local. Now, I think the importance of the bispectrum in that, at least the different groups, has varied. What is the sort of internal SphereX point of view on how important is the bispectrum to your measurement? Is it essential to hitting your target? Is it would be nice? Like, what are your turtle sort of point of view on it?
So I think I would refer to Chen, who is over there, who just published our official forecast. Who published our recent forecast on SphereX using multitracer bispectrum, which is consistent with what we had in the proposal. But so it's all the details. Chen, really, you could talk to Chen and she will give you the details. For us, we found that using the multitracer with the assumption about Kmax, we use bispectrum held by a factor of, is smaller by a factor of 2 as compared to the power spectrum. So it is definitely essential in reaching this target. That's what we found, and we can compare the detail of the forecast, but that's the basis of this limit. Yeah.
Down by a factor of 2, or that half, twice as much information.
So like the combination of power spectrum plus bispectrum is factor of 2 smaller than power spectrum alone. Yeah. Yeah.
Okay, thanks.
Again, you should really talk to Chen over there for details.
Okay, everyone can go talk to Chen after the.
Raise your hand.
Sorry. Okay, next targeted question. I was going to ask Marlena about, so Marlena, on your slides, you had this sort of other physics that looks like biasing that introduces scale-dependent biasing. So some of those are exciting signals like cosmic neutrinos, but I know there are other sources that can be concerning. Like, what is your sort of list of, these are the things that look like scale-dependent bias that I would worry about or be excited about or all fit into the same bucket?
So I think, so from what we studied, and this is a paper led by Chirhus Shavashwarkar in collaboration with Matt McQuinn and Tice Brinkman. We studied a few examples, nothing, as somebody asked Oliver earlier, I forget, about disentangling different signals, and FNL is the only thing that gives you this 1/k² correlation with the potential, but the point is you have a finite number of modes, and you have some signal that grows as you go to low k, so how well can you measure like 1/k versus 1/k² versus something else? And the thing that seems to be the most challenging from those analyses is something that was pointed out by Matt McQuinn and collaborators, which is that if fluctuations in the ionizing background modulate, for instance, through changing the temperature of gas and changing gas cooling, give large-scale modulations in the abundance of galaxies, that's a horizon scale signal. And the challenge there is similar to this B-phi challenge, which is how do you know the bias of your observed number of galaxies in terms of the fluctuations in the ionizing background. So for a given change in the ionizing background, how much does that modulate galaxy formation? And that's a very astrophysical question that I'm like not the person to address how precisely that's understood. And so in principle, their first paper on this showed that, you know, if you have complete uncertainty in that parameter, you could try to extract that from astrophysical simulations, but you don't really know what it is. You need to know a lot of subgrid physics, and then it really screws up your FNL forecast. But what we found is that parameter is probably not order 1 because we don't see that. It might, and if you put reasonable priors like 10% or something, you know, that bias factor is like 0.1, then it shouldn't degrade the constraints too much, but you should take it into account. But that's definitely the most concerning. The other signals that are of new physics, at least on a case-by-case basis, I think you can model it, and it's a gravitational signal, so you will have better control over it theoretically, because yeah. Does that answer your question?
Yes, thank you. Okay, next targeted question, Matthias. So you have seen a lot of progress in non-Gaussianity, starting with the CMV through, so you had a lot of role in bringing things to life, both in CMV and large scale structure. What do you think are things that we're not doing today that, you know, 10 years from now would be interesting analyses, or things we might be able to do that we're currently not doing that would improve our prospects of measuring non-Gaussianity?
I guess I'm old. That's what you were telling me in the question. I've seen a lot since the pyramids or something. Yes. No, I think I'm pretty optimistic that the things that we are doing make a lot of sense. I think things that I think have been quite particularly useful are these challenges that the blind challenges that people have been doing. The ability of outside groups to reanalyze things, I think, is pretty important. So I think the more open we are, the more willing to have different groups do it. I think it's good, and I think we have a good list of things to calculate, and I think we're in reasonably good shape, but I think it's a very difficult project. So I don't know if it's doable, but it's very interesting.
Okay, this is a follow-up question, and is going to be a question for Ben in a second. Are we all just going to be doing simulation-based inference or something like it in the future, or low-point correlators? Still, 10 years from now, we're still doing low-point correlators to measure non-Gaussianity. So I'm going to start with Matthias, and then I'm going to start with Matthias, and then I'm going to ask Ben the same question.
Well, so the point is if we go for the target, FNL equilateral of order 1, this is a sub 0.1% effect, and so other than integrals by hand, it's quite difficult to do this kind of precision. And simulations, I don't think we do have. If we were observing dark matter halos, I may buy that we can do simulation things because these are first principle simulations. Other than that, in addition to the computational expanded, I mean, it's not easy, but I know nothing about it. But from the outside, it looks the progress is difficult. It's hard for me to imagine that you can really get this level of precision. But of course, it's good to be able to do examples of such galaxy formation models to make sure that other things that you've developed make sense and give you reasonable numbers and so on. But that this would be based on simulations, the 0th order analysis in the next 10 years or 15 years, I find it hard to believe, but it would be great if it's the case.
Okay, Ben, do you have a rebuttal agreement?
So first of all, I don't think these two things are exclusive. I already mentioned before potential hybrid approaches that leverage the strength of perturbative approaches on large scales and the ability to simulate on smaller scales. Now, I also agree that simulations, are always going to be some approximation to reality, just like analytical calculations. The nature of the approximation is different. And so I think you can phrase it as an opportunity or as a problem that I think we're as cosmologists and astrophysicists, we're interested in understanding the small scale physics at ever increasing degrees of accuracy and sophistication. And so building more and more, better and better subgrid models, for example, that's something that, that's currently ongoing. And I think if we're looking into the future, the simulations will get better. The hope is that we can identify regimes where the simulations are robust, that don't necessarily depend on getting everything completely right. And that's, I think, an underappreciated aspect of simulation-based inference, that we have so much more freedom of choice of the kinds of statistics or the kinds of quantities that the observables that we can compute. I think if you limit yourself to 1.2.3 low order correlation functions, your view of the world is necessarily limited. It's a very nice way to organize the computation, but it's not clearly always the best way to address your choice of observable. So, for example, it may be true, and these are things that we're just trying out now, and so I don't have the answers yet, but it may be true that, for example, in certain density regimes, maybe we can go much further in K and be fine. So maybe, but just we avoid the highest density regions, or maybe we avoid the lowest density regions, or that might have consequences for what we consider reliable K modes. Those are not questions that you can ask if you're limiting yourself to particular kinds of, just 2 or 3 point statistics. The ability to cut the data in much more refined ways than simply kind of cutting off at some K scale. You can cut in a different basis set or after some post-processing that particularly addresses uncertainties in your simulation model. Of course, to anticipate the response, yes, maybe you can do this in an organized way if you know all the uncertainties. What about the unknown unknowns? Sure, but I think that's where we're going to be able to test against actual data, right? We'll see data that are rich, that we can check whether our models can predict those data. There are ways to confront data sets with models and evaluate the goodness of fit and evaluate different simulation models, how well they fit observations. And that's also something that's becoming much more feasible now with these machine learning driven approaches. So I think we're going, and again, I'm not, I think that, clearly on large scales in the perturbative regime, let's say the traditional way of approaching the problem, or the theoretical way of approaching the problem in terms of endpoint functions, is a very well organized and clearly defined way of organizing the computation. But I think we're really undergoing a sea change, I would say, in cosmology in terms of the richness of what observables we can define and how we can address these questions by using a broader range of tools.
Okay, thanks, Ben. Okay, I'm going to ask one more question, and then I'm going to turn it over to audience questions. Okay, but I'm going to ask that everyone answer this one. Okay, so of your inflationary targets that were outlined by Austin, or you can pick off the board, but for example, FNL local, FNL equilateral, which do you think is the most exciting science target for the next generation of large-scale structure surveys? Matthias, you're holding the mic. You can start.
It needs to involve FNL orthogonal. No, I think FNL equilateral of order 1, I think it's the target I would pick, also because I think it's the most ambitious one. Of the things that we can write down, and so I think that's one I would pick.
All right, I would pick FNL local because as a close-up, it can happen in the coming years, coming decade, let's say. And especially if we can leverage, the B5 multitracer, if we find a way to do that in practice, we'll have FNL of 1. We'll have uncertainties substantially smaller than FNL local of 1. And that's so it makes sense to focus on that, and that's really exciting. We can actually do it right now. I mean, in the coming years. So.
We're not waiting by
Whatever
like
metric you would like.
data, like, okay. I think I'll pick FNL equilateral as well, just because I think it's I think as a theoretical target that is quite interesting. But I don't, do I have more to say? No, I think FNL local of order 1 could be comparably interesting. I mean, how do we know that the inflaton is alone? Why should it be alone? I always found those models a bit contrived, but once you actually go to FNL of order 1, I don't find it so contrived anymore as like needing, as the scenarios where you boost it a lot. So yeah, but that's exciting.
Okay, Ben, you're last.
Features, of course, for you, Dan.
So, there are too many panelists because out of the limited number of choices, I think everything has now been mentioned. But if we can be very futuristic, you could say that the generic, even single field models predict a small FNL local, and this may be quite small, but but it's this I think will be the ultimate target of confirming maybe sort of at similar level to R, but maybe the uncertainty about what the value is there is much less because we do have a generic size scale but that's another target that will be a couple of orders of magnitude below FNL of 1 local. But who knows? It's not known. I don't think anybody can say whether we have enough information in the observable universe to get to that point, given the uncertainties in the systematics. But I think that would probably be the ultimate goal or target.
Awesome, thanks. Okay, so thanks. Thanks to all the panelists for entertaining my questions. I think Mark is already ready for the follow-up.
So I just want to make 2 comments. First, I'm completely mesmerized by the recursive panelists on the Zoom screen. Second comment about your question about how are we going to know that we should trust this in the future. There's something that might be different 10 years, 20, 15 years from now, which is that, our colleagues in neutrino physics are actually doing experiments to measure neutrino masses. And it's not inconceivable that we will know what the neutrino masses are with some precision. And that's another piece of the puzzle that we can use to calibrate on. Right now, we're trying to fit all of our models and the neutrino mass. There was a paper about this by my colleague Surjit Rajendran and 3 other people last week. In the future, you should be able to just, use that neutrino mass, measure neutrino mass to see if your analysis, if your model makes sense. So it's not going to necessarily be a sea change, but there will be more information from physics that we can use to narrow the range of possible models.
So several people have mentioned about this GRFX, or sort of a projection onto the light cone, and several calculations come out, so it'd be over the 1. But I was wondering if anybody has calculated the variance of that number. In other words, can I just take the prediction from a paper and subtract it off? And how much does it depend on the actual realization? And if it depends on the realization, can I do something like, can I de-lens the data, or can I de-Sachs-Wolf the data, or something like that? Has anybody looked into this?
No, not that. I mean, it's a good question. I think we discussed that in the past, but it hasn't been done yet. Yeah, and that's a big, important question.
Because I would imagine if cosmic variance of order 1 and you don't know the realization, then you're stuck, right?
Yeah.
Sorry. Okay. I don't know about that, but isn't it not a stochastic quantity? I thought it was just a statement about how you relate the observables to the same. I thought there was still like one potential degree of freedom, or like one scalar degree of freedom that sets the amplitude of, the signal on large scales. So why would it depend on the realization?
Oh, I imagine it would depend on the potential on the light cone all the way to the observable or something, right? So, then it
sorry,
depends
some projection.
Right.
Okay.
Mhm.
Okay. Thanks.
But can't you assume that it's Gaussian and then compute it?
At the moment, we are talking about measuring with spec S5, FNAT collateral, maybe order 10 or so, being optimistic. Maybe probably more like 20 or 30. Line intensity mapping a bit better. So getting to order 1 will definitely be very difficult, also very expensive. If you're not finding anything with the upcoming experiments, how can we go to the funding agencies and tell them it's worth it? What for you is there a threshold somewhere?
Yeah, I guess it's not exactly your answer to your question, but it's a similar feeling. It expresses a similar feeling that I had when I was listening in this morning. This idea that we want to do, or the doing 10 times better than DESI, it doesn't seem to me ambitious enough. It would need to be at least 10 times better than Planck, right? I don't know. And for sure, that would be the goal. I don't know, maybe you need to make the survey 10 times bigger or something. Sorry.
We'll meet back here at 4.